Now that we have some experience with continuity, we're going to transition into a more stringent form of it. One of the features of our definition of continuity is that it functions pointwise. That is, we check for continuity at each point separately. Let's take the graph of f of x equals 1 over x to see how this works in practice. Remember that we prove continuity at a point by creating an epsilon band and trying to find a delta band such that all the points on the graph lie within both the bands. If we take a point on the graph towards the right where the graph is flatter, we can use a fairly wide delta. But if we pick a point further to the left, the delta needs to be much smaller for the same value of epsilon. This shows that the choice of delta depends on exactly what point you're looking at. Uniform continuity attempts to use one delta for all the points. Definition: let f be a real valued function defined on a set S. Then f is uniformly continuous on S provided that for each epsilon greater than 0 there exists a delta such that x and y in S and the absolute value of x minus y less than delta implies that the absolute value of f of x minus f of y is less than epsilon. This definition is very similar to the definition of continuity, so it's important to understand the differences. We will compare the definitions of continuous on a set S with uniformly continuous on a set S. The function f is continuous on S provided that for each x naught in S and epsilon greater than 0, there exists a delta such that x in S and the absolute value of x minus x naught less than delta implies the absolute value of f of x minus f of x naught is less than epsilon. The function f is uniformly continuous on S provided that for each epsilon greater than 0, there exists a delta such that x and y in S and the absolute value of x minus y less than delta imply the absolute value of f of x minus f of y is less than epsilon. If you look at everything after the such that, there's very little difference between the two. It almost looks like you just replace x naught with y. However, compare where x naught in S appears in the definition of continuous compared to where y in S is declared in the definition of uniformly continuous. Continuity requires the choice of x naught at the same time as the choice of epsilon, so that it's a fixed value when picking the value of delta. However, uniform continuity starts off with just an epsilon, and the choices of points comes after the delta has been chosen. This is a very subtle, but very important mathematical distinction. Uniform continuity controls the amount of variation that a function can have. Once the value of epsilon is chosen, the value of delta is fixed, which means you can have a rectangle that is used to measure the variation. As long as the rectangle can be drawn narrowly enough so that the function always comes out the side of the rectangle and not the top or the bottom, the function is uniformly continuous. Here are some examples to try to build some intuition about uniform continuity. We've already seen that the function 1 over x is not uniformly continuous. This is due to the steep slope on the left-hand side. However, this doesn't mean that an unbounded function can't be uniformly continuous. The straight line function f of x equals x is uniformly continuous. In fact, all linear functions are uniformly continuous. The function f of x equals x squared is not uniformly continuous. As you go to the right, the slope gets steeper and steeper, much like the slope of 1 over x. However, a steep slope, even an infinitely steep slope, isn't enough to negate uniform continuity. The graph of the function f of x equals square root of x has an infinite slope at the origin. The difference is that the interval where the slope is very steep is also very small. It's possible for bounded functions to fail to be uniformly continuous. The function f of x equals sine 1 over x for x greater than 0 is bounded between -1 and 1, but because the values vary between -1 and 1 infinitely often as x approaches 0, this is not uniformly continuous. However, the graph of f of x equals x times sine of 1 over x turns out to be uniformly continuous. The slope actually alternates between -1 and 1 infinitely often, but the variation in the values of the functions is being squeezed down to 0 since we're multiplying by a value that's approaching 0. As these examples show, uniform continuity has some nuances. It turns out that uniform continuity is important for integration. It's not immediately clear what any of this would have to do with integration, but is related to trying to help upper and lower bounds for the area under the curve to converge. We will see this in the second semester of real analysis.